Hello everyone, how are you doing today? I hope you are all very well in both health and spirit. In this presentation, I will talk about the oxidation of nitric oxide or NO gas on platinum-based materials. An important application of this study is on the exhaust gas purification systems. Finding ways to improve air quality has been a continuous challenge to mitigate environmental stressors. So the importance of addressing this challenge is ever increasing in our modern society, as the amount of exhaust gas from a variety of combustion systems increases with economic growth and human population. NOx or NOx, such as NO and NO2 gases, are considered to be major contributing factors in air pollution because they are noxious and directly contribute to the formation of acid rain, photochemical smog, and particulates in air. There are a number of techniques for removing NOx in combustion systems. In diesel oxidation after treatment, a diesel oxidation catalyst oxidizes NO to NO2 under oxygen-rich or lean burn conditions to induce the fast selective catalytic reduction of NOx with ammonia. Another approach is the use of NOx traps or NOx storage reduction systems, which operate under the cyclic fuel lean and fuel-rich conditions. In these systems, NO reacts with oxygen to produce NO2, which subsequently adsorbs on the storage material as a nitrate in fuel-in operation. In these systems, NO reacts with oxygen to produce NO2, which subsequently adsorbs on the storage material as a nitrate in lean fuel conditions. This nitrate then reduces to harmless nitrogen gas under fuel-rich conditions. Both of these techniques rely fundamentally on the catalytic oxidation of NO into NO2. Supported platinum is typically used as the NO oxidation catalyst in conventional exhaust gas purification systems as well as in kinetic experiments. However, since platinum is an expensive noble metal, it is desirable to decrease its amount in the production of the catalyst while at the same time improving its catalytic performance. An important first step in doing this is to elucidate the reaction mechanism of NO oxidation on platinum so that meaningful insights can be gained into the rational design of the catalyst. We performed such study and reported our results in this particular cited paper. However, since it is a lengthy discussion, I just show here a summary of what we have learned from our study of NO oxidation on pure platinum surface. So what did we learn from platinum? We have found the following two key features. First, O2 dissociative adsorption is the rate determining step. Second, surface NO+O yielding NO2 via the Langmuir-Hinshelwood mechanism reaction is endothermic because of the strong platinum-oxygen bond. The reaction energy and activation barrier are given by the following values. So a desired catalyst is the one that promotes the non-activated or the one that has lower activation barrier for O2 dissociative adsorption, and at the same time, it should promote a weaker platinum-oxygen bond. I show here a typical energy profile for the dissociative adsorption of oxygen molecule on the surface. The activation barrier is given by the height of this curve, while this minimum point gives us a binding energy or adsorption energy of the dissociated atoms with respect to the reference state. As I've mentioned in the previous slide, the desired catalyst is the one that promotes a low activation barrier for the dissociation, and at the same time, the binding of the dissociated oxygen atoms on the surface must be weak. However, it is typical that decreasing the adsorption energy also increases the activation barrier. Interestingly, our group has previously found that a type of platinum-based material wherein a monolayer of platinum pseudomorphically laid on 3D transition metals can promote a lower activation barrier for O2 dissociation and weaker adsorption energy of oxygen atoms. We can look at this system as a larger cluster size limit of a core shell nanoparticle where the core is a 3D transition metal. I show here the energy profile for oxygen dissociation on the surface for the case of pure platinum given by the black curve as well as platinum cobalt and platinum iron bimetallic systems. It can be seen that for the case of platinum pseudomorphically laid on iron can provide no activation barrier for the dissociation of oxygen molecule, and at the same time the binding energies are also lower compared to pure platinum. So how do these bimetallic systems promote a lower activation barrier for O2 dissociation? We take note that the dissociation of oxygen molecule on the surface is facilitated by the donation of electrons from platinum D states to the pi star molecular orbital of oxygen molecule. The dz orbital is an important component of the platinum D band because it protrudes out from the surface and is spatially compatible with oxygen pi star antibonding orbital. It was found that for platinum on iron system, there is a highly polarized spin-down dz. This characteristic of the dz orbital can promote a more effective hybridization with the O2 pi star antibonding orbital. Let us now discuss the adsorption of oxygen and NO species. In the case of pure platinum 111 surface, the adsorbates oxygen and O2 bind at the FCC halo sites. NO binds on the surface via the nitrogen with the NO bond perpendicular to the surface. This agrees perfectly with other DFT studies. Surface oxygen can be formed through the dissociative adsorption of O2 gas and or reverse NO oxidation, which is the decomposition of NO. Our calculations found activation barriers of 0.26 and 0.02 electron volt for O2 gas dissociative adsorption and reverse NO oxidation via the Langmuir-Hinshelwood mechanism, respectively. Oxygen formation via the latter is thus more kinetically favored over the former. This is consistent with modeling studies which found that O2 gas dissociative adsorption can potentially limit the overall surface reactions. Oxygen and atom formation through the reverse reaction of NO oxidation via the iliradial mechanism has a large activation barrier, which is about 1.57 electron volt, and is thus kinetically less favorable. Similarly, an adsorbed NO molecule can be formed through the adsorption of NO gas and or the reverse Langmuir-Hinshelwood mechanism for NO oxidation. The former is non-activated, which means that it has zero activation barrier, while the latter has a very small activation barrier as mentioned earlier. For the platinum M bimetallic systems, both oxygen and NO adsorb at the bridge site. The binding of these species on the bimetallic systems is weaker than that on pure platinum. The magnitude of the decrease in adsorption energy of oxygen and NO with respect to the adsorption energy on platinum is shown in this figure. The weaker binding of these species on the bimetallic system is attributed to the broadening and downward shift of the platinum D band in the bimetallic systems. This is a trend that is also observed in the case of other adsorbates. Let us now turn to the adsorption of NO2. NO2 can adsorb on the surface in the configurations known as micro NO nitrito, OO' bidentate, and nitro structures. The nitro structure has the weakest binding to the surface for all the surfaces considered. This figure shows the adsorption energy of NO2 on the surfaces with respect to the nitro structure. In the case of pure platinum, the micro NO nitrito and OO' bidentate structures differ only by 0.08 electron volt, with the former being more stable. However, for the bimetallic systems, the OO' bidentate structure is more stable than the micro NO nitrito structure with an adsorption energy difference of 0.01 to 0.09 electron volt. Note that the trend in the change of adsorption energy of NO2 from micro NO nitrito to OO' bidentate structures follows the trend of the increasing Bader charge of NO2 OO' bidentate structure on the bimetallic systems, as I will show later. The stabilization of the OO' bidentate structure on the bimetallic systems can be explained by the hybridization of the frontier NO2 molecular orbitals with platinum D states. The highest occupied molecular orbital of gas phase NO2 is a half-filled spin-up 6A1 orbital, as shown in the charge density difference for NO2 adsorption on platinum for OO' bidentate and micro NO nitrito structures. The binding of NO2 on the surface is characterized mainly by the interaction of the 6A1 NO2 orbital with the platinum D states. This interaction is maximized when NO2 adsorbs via the OO' bidentate configuration because the 6A1 NO2 orbital has the correct symmetry and orientation to interact with the platinum D states at this adsorption configuration. Thus, the strength of the binding of NO2 via the OO' bidentate configuration is determined by the platinum D donation into the half-filled 6A1 NO2 orbital. In the case of the bimetallic systems, the platinum monolayer surface is converted into an electron-rich surface because of the charge transferred from the 3D transition metals. As shown in this table, platinum has gained 0.33 to 0.55 electron from the 3D metal substrate. This promotes the charge donation from the platinum D states into the 6A1 NO2 orbital, which stabilizes the OO' bidentate configuration. As shown in this table, NO2 has gained more charge in the OO' bidentate configuration than in the micro NO nitrito structure for the monolayer bimetallic systems. Therefore, in an electron-rich platinum surface, the OO' bidentate configuration is more stable than the micro NO nitrito structure. This can be verified in the case of the platinum bilayer on 3D metal substrates. As shown in this table, the platinum surface atoms in the platinum bilayer system have very small excess charge comparable to those in pure platinum. As such, the stabilizing effect of the electron-rich surface on the OO' bidentate configuration on platinum monolayer case is not observed. That is, the micro NO nitrito structure is more stable than the OO' bidentate configuration on these platinum bilayer bimetallic systems, just like in the case of pure platinum. Thus, the relative stability between the two structures depends on whether the OO' bidentate structure is stabilized or not. The reaction free energy change ΔG and activation barriers can describe the thermodynamics and kinetics of NO oxidation on the surface. In this slide, I will discuss these values for the NO+O yielding NO2 reaction via the Langmuir-Hinshelwood mechanism. I show in this figure the initial, transition, and final states for NO oxidation for the case of pure platinum and platinum on iron to represent the bimetallic systems. In the case of pure platinum, the reaction proceeds via the surface diffusion of both NO and oxygen until the micro NO nitrito is formed. This reaction requires a large activation barrier, which is about 1.24 electron volt, because oxygen and NO are strongly bound to the surface. To illustrate this, our calculations found diffusion barriers of 0.69 and 0.39 electron volt respectively for oxygen and NO diffusion between two neighboring FCC halo sites on platinum. For the bimetallic systems, the NO molecule rotates from the surface perpendicular NO bond in the initial state to the surface parallel NO bond in the transition state along the reaction path. In another study, we reported such surface parallel NO orientation to be the transition state for NO dissociation on copper. We found that the difference in the adsorption energies of adsorbed NO in the surface perpendicular and surface parallel orientations is only 0.24 electron volt for platinum iron system to represent the bimetallic systems and 0.54 electron volt for pure platinum. Thus, it is easier for NO molecule to rotate on the bimetallic systems than on pure platinum. Also, note that since oxygen and atom is more weakly bound on the bimetallic systems than on pure platinum, it is easier for oxygen and atom to diffuse from the bridge site to the next stop site to form NO2. This results in a lower activation barrier for the NO bond formation on the bimetallic systems compared to that on pure platinum. The calculated activation barrier versus the reaction free energy change, also known as the Brønsted-Evans-Polányi Plot, for NO oxidation is shown in this figure. A similar linear relation between the activation barrier and the reaction enthalpy was shown for NO oxidation on platinum skin on 4D and 5D transition metal substrates reported by another research group. A large activation barrier and a slightly endothermic reaction free energy change are seen in the case of pure platinum as previously noted. while the bimetallic systems promote a lower activation barrier and an exothermic reaction-free energy change compared to pure platinum. Thus, NO oxidation is thermodynamically and kinetically more favorable on the bimetallic systems than on pure platinum. So in this presentation, I have shown that for NO oxidation on pure platinum, the surface NO+O yielding NO2 reaction is endothermic, and the O2 dissociative adsorption is the rate determining step. However, substituting the lower layers of platinum with 3D transition metals can promote an exothermic NO+O yielding NO2 reaction and non-activated O2 dissociative adsorption. This is because of the downward shifting and the spin polarization of the platinum D band. So with that note, thank you so much for your kind attention, and I wish you the best for your research endeavors.